Hello everyone. Now I'm going to discuss on the topic machine learning based content filtering for spam email classification. Our team members are Vamsi Krishna, myself Pujita and Gautam. Yeah. Coming to introduction, the rise in the internet usage has led to a surge in email spam, particularly regions like Asia and North America, causing network congestion, wasted time, compromised privacy, and increased exposure to phishing and malware threats. So, the machine learning models such as support vector machine provide a highly accurate and adaptive approach to classify the emails as spam or ham, outperforming the traditional filtering systems as well. Coming to abstract, the aim is to develop a machine learning model using the techniques like support vector machine to accurately classify the emails as spam or ham. This enhances email security to efficiently filter out wanted or malicious messages, improving the protection against the spam related risks as well. The proposed model offers a highly level of accuracy in classifying the emails compared to previous models, making it so a reliable solution for protecting the users from spam. For example, a spam email might claim to be from a bank, asking you to verify the account details, avoid the suspension, which is an attempt to steal the sensitive data. So these emails can slow down the internet connections, tamper with search results, and pose security risks. So, to tackle these issues, a machine learning model such as support vector machine can be used to classify the emails as spam or ham. By analyzing the email content, the model accurately filters out the spam emails, offering the better protection and improving the email security. So now, coming to data pre-processing, this is one of first step to execute the SVM model that we are implementing. So this is mainly used to like raw email data is noisy and unstructured. So pre-processing transforms the text into a clean format suitable for machine learning models, and it reduces the words and help the model to increase the accuracy. So coming to the tasks that are in NLP are lower casing, remove special characters, remove stop words, remove punctuations, and stemming. So, lower casing, it converts all text into lowercase to ensure the uniformity. For example, the capital letters spam and the capital letters SPAM and lowercase letters SPAM treated alike. So, coming to remove special characters, it eliminates the non alphanumeric symbols like at the rate, hash, and exclamatory. So keeps only the essential data for analysis. Now, to remove the stop words, it filter common but insignificant words like and, is, the, etc. It mainly focuses on the meaningful content. Coming to like stemming, it is a process of reducing the words to their root form by removing the suffix, such as turning, running into run or turn. It simplifies the words to their base from where it will lose the meaning, unlike lemonization, which considers only the context. So it is quick and may lack the accuracy. And like we use tokenization and lemonization to convert the words. So the first topic is tokenization, where the tokenization is a process of splitting a text into smaller units called tokens, which can be words, phrases, or symbols. It is a foundational step in natural language processing to transform the raw text into structured data for further analysis. For example, The sentence, my name is Pujita, would be tokenized into tokens by dividing the line into words like my name is Pujita. So, coming to the next topic, lemmonization. So, generally, it converts the words to their dictionary form. So, lemmonization is a process of reducing words to their dictionary form called the lemma. Unlike stemming, which simply truncate the words, lemmonization considers the context and part of speech to determine the correct lemma. For example, several emails collect data and then from the data it will take the words and lemonize it. Like better is lemonized as good and etc. So depending upon the context, it changes the words as needed. So it is more sophisticated and accurate than stemming as it involves the linguistic analysis to ensure the word's correct meaning is preserved. However, it can be more computationally expensive due to the need of dictionary lookups and context analysis. And most knowingly, this context aware and it is precise. So, from next topic, my friend will continue.
Hello everyone. My name is Vamshi and I will continue the presentation. So the model we have discussed so far in the paper was support vector machine. So as of now, as so far we discussed about the data pre-processing. So after doing all the steps that Pujita has said, uh, we'll get a very prescribed data. From the data set, we're gonna for the data set, we're gonna apply the support vector machine model. So, so yeah, the database can be in two types. The first one is linearly separable. The data can be easily separable, and the second one is linearly non-separable. We're gonna discuss it more further in the coming slides. So, coming to the first database structure, which is linearly separable data. So, SVM uses these four functionalities to 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 train the model and to get the accuracy. So the first one is binary classification. So it is divided into two classes. The first one is positive data and negative data. So like in the binary classification, so the data points are kind of divided into a positive set of data is divided into one part, and the negative set of data is given to other parts, so that we easily find out which one is spam or which one is harm. And the second functionality used is for the linearly separable data is feature space. So in this case, the data points are represented as a vectors in the each feature space. So it is located as in a graph structure, and each point is located as a vector, so that from those vectors we're going to divide it by using an hyperplane. So the third functionality is hyperplane, as I discussed in the second functionality. The hyperplane divides the classes into two parts. Coming to the fourth functionality, which is support vectors. The key data points close to the hyperplane improves the model generalization. So here are the figures, you can look into it. So here the blue dots are considered as normal emails, and the red ones are considered as spam emails. So firstly, seeing the right side of the image, you can figure out how the hyperplane was designed. So they are designed the four different lines of hyperplane. So based on that, the left side image will show you the proper representation of hyperplane and proper discrimination of dividing both uh, positive labels and negative labels. So let's discuss this left side image more clearly. So here the L1 is a hyperplane which need to be very much close to the positive label, and L3 is a hyperplane which need to be very much close to the negative label. So from the both L1 and L3, we're gonna decide L2 hyperplane, so that it will properly divides the positive labels and negative labels uh, correctly. So here is how the SVM look like for the linearly separable data. So the first thing is we need to find out the two support vectors. So each support vector, the closest support vector, we need to draw a line, the two further lines, and based on the two lines, we're gonna decide the hyperplane, which is a maximum. which is a maximum margin, and a positive hyperplane. In this way, we'll maximize the margin here. So use of dot product in the SVM. So let's discuss how this dot product gonna help SVM to design an hyperplane. Considered a point X, and we want to know whether it lies in the right side of the plane or left side of the plane. So considering X, here you can see the black point is represented as X, and we need to draw a perpendicular line to it, which is W. So from that, here are the equations you can find out. X dot W equal to C, the point lies on the decision boundary, which indicates that if you got X dot product of W is C, then you can say that the particular point is perfectly aligned to the hyperplane. If suppose X dot W is greater than C, which represents that it is more further to this positive sample, and we will consider that point as a positive sample, and which is a correct email. If suppose X dot W is less than C, which we will consider as a negative sample, and which more likely, which is on the negative sample space, so we will consider the male as a negative sample male. So the margin in support vector machine, the equation of hyperplane is W dot X plus B. So now let's discuss the hard margin and soft margin in this slide. The hard margin will help us to figure out the hyperplane for the linearly separable data. We use the soft margin for the linearly non-separable data. As you can see the differences between both the diagrams. In the first diagram, all the labels are perfectly aligned. The positive labels are perfectly on the left hand side, and the negative labels are perfectly on the right hand side. Where you can see in the soft labels, soft margin, left side of the hyperplane, there is one negative label, and when you consider for the right side, you can find the two positive labels. So this is a linearly unseparable data. We cannot divide the data into perfectly off. So there are the cases like there are very minute changes can be considered in the soft margin. So let's discuss the hard margin, which is linearly separable data. So we need to consider a point which shows on the particular point on the left side of the hyperplane, and we'll consider a distance between x2 and x1. Here you can see perfectly in this image. So all the red points which the equation satisfied, W dot product of x bar vector plus b should be negative for the red points, need to be red point. For all the green points, W vector dot x bar plus b is greater than equal to 1, which is considered as a green points. So the argmax W star and B star 2 by W will represent a proper maximizing hyperplane. From this equation, from the engineering analysis equation, you can find out the hyperplane in the support vector machine for the linearly separable data. So coming to the SVM for linearly non-separable data. So here you can see the example of a linearly non-separable data. Here you can see all the violet labels are in the center, and you can find again other circle of yellow other labels. So here it is very much difficult for us to draw a hyperplane in this case, and also we cannot maximize or minimize the hard margin in this case. So for analysis, we use the three functionalities in this linearly non-separable data. The first one is soft margin, and as we have discussed earlier, the soft margin, how we can margin it in the more clear. It allows a miscalculation, balancing margin size and errors with the C. The C is a parameter. We going to discuss it more further in the next slides. Kernel trick. So it maps the data to a higher dimension for linearly separable. So there are the different kind of kernel tricks here. So based on the structure, based on the labels, we're going to decide which kernel we need to use. So let's discuss everything in the next slides. Support vectors, as we have discussed this in the linearly separable data as well. So these are the points which represents each as a vectors, and which will help to maximize the margin while allowing the misclassifications. Soft margin SVM. So this is how a real world scenario really perfectly linearly separable. So there are some cases like, as we discussed, linearly non-separable data, where the support vector machine addresses this challenge effectively by modifying the classification equation to allow some misclassification, enabling the robust handling of complex data. So as we known that for the hard margin, we're gonna do argmax. So for this case, we're gonna consider it as 1 by fx, and we minimize it. It's a vice versa process. So in the same way, when we consider f of x as not f of x, like we considering it as 1 by f of x, so we're going to minimize it. So here you can see the arg minimum of w star b star into modulus of w by 2 should be in the range where wi and w vector and dot product of x bar plus b should be greater than 1 to fit into the softmax. So here there is a difference between argmax and software varies here. We're going to add some error to this. So this error will help us to find out the proper hyperplane of the non-separable data, so that it will perfectly figure out the spam emails and non-spam emails. So here you can see the variation between, here you can find a variation between the soft margins of the two different diagrams. Here the first diagram, we are like maximizing the hyperplane as much as possible, because the labels are being misclassified. Like there are two labels in the left side of the red labels in the left side of the positive labels, and there is one label in the right side of the positive label. As much as we maximize it, we're gonna get a proper hyperplane. Whereas the figure 2, it is linearly separable data, so we need to minimize the hyperplane as much as possible. So here, depending on the data set and depending on the labels, we need to figure out which margin we need to draw. So choosing between the models is maximum margin. Two misclassification points are often one with a smaller margin, and no misclassification depends on the priorities. So SVM error combines a margin error and classification error. So here in the softmax, as we discussed, we need to add some error so that it will perfectly describe an hyperplane parameter. So here let's discuss the important support vector machine for non-linearly separable data is kernels. So here you can see the left right side image, which is a linearly unseparable non-separable data. So as you can consider the left image, we need to make it as seen in the left image. We need to make sure to keep it in a linear motion, as keeping all the positive labels aside and keeping again converting the negative labels in the center and getting the positive labels again to the left side. So in this way, we can at least find out some consequences and consistency in the spam emails or non-spam emails. So here is other example of the kernel, which is a 3D, like which is a quadratic equation, as this is the previous one, which is a linear equation, and this is this is like a 3D image. As you can know, the data points, the negative labels are in the center, and every positive label was covered with the covered to that negative labels. So as you can see in the right side image, the negative labels have been taken up, and which based on the 3D image, it is considered as we can show, the decision surface can be created there. So in this way, we can divide them for the nonlinear separable data using kernels. Let's discuss the types in the kernels. The first one is polynomial kernel. So using the equation f of x1 comma x2, x1 transpose in x1 transpose matrix in dot product of x2 plus 1 should be uh, transpose of D. So this is the equation. From this equation, we can figure out a curve in the positive labels and negative labels. This is a general polynomial kernel. Let's discuss the sigmoid function, which is f of x1 comma x2 equal to tan h of alpha into x transpose y plus x. Here you can see this is another representation of dividing the non-separable data. And the other kernel is RBF kernel, which is a very important kernel, which will help us to figure out or remove some of the most intermixed positive labels. Here you can see the green side was represented as a positive label, and the creamish side which represents a negative label, and the violet side will be removed completely, because there are equal number of chances for both positive labels and negative labels. So here is the equation, exponential equation we use to figure out the graph. So here is the architecture that we are using in the spam mail detection. Firstly, the incoming mails, all the incoming mails, we will consider it and we will analyze it. We do data pre-processing in this case, and we make it a raw data, from the raw data to proper data pre-processing data, and we extract the features in it. Based on the features, we'll design a model, SVM model. Based on the SVM model, we're gonna provide the results to the user, whether the mail is spam or ham. So let's the next slide will discuss by my friend, the next slides.
Hi everyone, I am Gautam. I'm here to discuss about the advantages of SVM. Coming to first advantage, SVM is an excellent tool for scenarios where we have limited understanding of the data or its distribution. SVM works effectively even with irregular or unknown patterns, and its versatility allows it to handle various types of data, including images, text, and audio, and making it applicable across a wide range of problems. Coming to second advantage, overfitting occurs when a model becomes too tailored to the training data, losing its ability to generalize to new data. SVM minimizes the risk by focusing on maximizing the margin between data classes rather than just fitting the data points. This characteristic makes SVM particularly effective for datasets with clear class separation, ensuring reliable performance. So, coming to third advantage, the core principle of SPM is to create the widest possible margin between different classes of data points. This high margin strategy improves the model's ability to handle new data accurately, even if additional data is introduced later. So, the focus of maximizing the margin enhances the generalization capacity of SVM that gives resulting in more robust and precise categorization. So coming back to the results, here this bar chart of accuracy, this bar chart comprises the accuracy of two machine learning algorithms. One is SVM, support vector machine, and other one is K nearest neighbors. From the chart, SVM achieves a significantly higher accuracy, that is close to 97%, indicating its superior performance in the given context. So on the other hand, the KNN on the has accuracy slightly above 95%, showing that while it performs decently, it is less effective than SVM. This comparison highlights SVM's ability to better classify data due to its margin maximization approach, making it a more reliable choice for the particular dataset. In contrast, KNN may struggle with complex patterns or large datasets as it relies heavily on local data points. Coming to the other bar chart time level, SVM requires approximately 15 milliseconds, indicating it performs faster in this context. On the other hand, KNN takes around 20 milliseconds, showing it is slower compared to SVM. It is same as compared in the other time level bar chart also. This difference arises from their computational processes. SVM creates a decision boundary during training, allowing predictions to be made efficiently. In contrast, KNN performs distance calculations between the test and data, all training points during prediction, making it more time consuming, especially for large data sets. Coming back to precision, this bar chart here, in this bar chart, the SVM model has a precision value close to 100%, indicating it performs very well in identifying true positive cases. On the other hand, the KNN model has lower precision value closer to 90%, suggesting it is less effective than SVM at making accurate positive predictions. Overall, bar chart demonstrates that SVM outperforms KNN in terms of precision. Coming to the middle chart, which has pie chart and bar chart, the pie chart illustrates the distribution of two categories, negative and positive. Negative makes up the majority, accounting for 86% of the total data. Positive represents the remaining 13%, showing that the dataset is highly imbalanced with significantly more negative cases than positive ones. Coming to this bar chart, the bar chart provides a count of two labels, ham and spam. ham is dominant with nearly 5,000 occurrences. Coming to spam, it is much fewer with less than 1,000 occurrences. So, combined interpretation, both charts highlight an imbalanced data set where negative ham cases vastly outnumber positive spam cases. This imbalance can be challenging for machine learning models. So, coming to conclusion, email is the most significant form of communication today, with over 270 billion emails sent daily. 57% of which are classified as spam. Spam emails, often unwanted commercial or malicious content, can damage personal information such as bank account details or harm individuals, businesses, or groups. They may also contain links to phishing sites or malware designed to steal data. This system aims to identify and filter these unsolicited emails, ensuring enhanced security and minimizing the financial and personal risks associated with spam. The proposed model achieves an impressive accuracy in detecting spams, offering highly accurate results through ongoing optimization. These are the references that were used in this paper. Thank you.